A very, a very good morning to one and all, distinguished guests, professors, and students. My name is Rishabh Rai, and I am a pre-final year student at NIT Jamshedpur.
I am Shivani Sagar and I too am a BTech student at NIT Jamshedpur. We will be the host for today's event. It gives us great pleasure to welcome you all to the celebration of 3rd International Conference on Advancement in Materials Processing Technology 2023.
Without any further ado, I would like to invite the guest of honor, Professor I. Manna, Vice Chancellor, BIT Mishra, Professor P.P. Chattopadhyay, Director, NEI AMT, Ranchi, Chief Guest, Mr. Yushi Mishra, JSW, BSPL, Professor Gautam Sutradhar Sir, Director, NIT Jamshedpur, and Chairperson, AMPT 2023, Dr. Ranjit Prasad Sir, to the dais. For the ceremonial lamp.
Shubham karoti kalyanam arogyam dhan sampada shatru buddhi vinashaya deepakay namastute deepo jyoti param brahma deepo jyoti janardhana deepo haratu me papam sandhya deepa namastute deepo jyoti param brahma deepo jyoti janardhana deepo haratu me papam sandhya deepa namastute.
Thank you, gentlemen. I would now request Dr. Ranjit Prasad Sir to escort the dignitaries to the dais.
Thank you, sir. I would now like to start off the event with melodious Saraswati song.
On behalf of the team, I now request Dr. Ranjit sir and Reena ma'am to present the token of respect to our guest of honor, Professor I. Manna sir.
He is joining online, and Professor P.P. Chattopadhyay sir, Chief Guest Mr. U.C. Misra sir, and Director sir as our token of respect. Thank you, ma'am. Thank you, sir. I now request our respected chairman, Dr. Ranjit Prasad, sir. Dr. Ranjit Prasad, sir, to give our guest of honor as a token of respect. Yes, sir. Thank you, sir.
Professor Deepak Majumdar sir.
Thank you, sir. Thank you, ma'am. I now request our respected chairman, Dr. Ranjit Prasad, sir, head of the Metallurgical and Materials Engineering Department, NIT Jamshedpur, to come forward and give a welcome address and a guest introduction.
So please.
Then introduction. ठीक ठीक परम वंदनीय भारत माता को याद करते हुए हम लोगों ने सरस्वती वंदना के साथ आज के इस इंटरनेशनल कॉन्फ्रेंस एडवांस मटेरियल प्रोसेसिंग टेक्नोलॉजी 2023 का शुरुआत किया है। आज हमारे बीच इस कॉन्फ्रेंस में मटेरियल प्रोसेसिंग रॉ मटेरियल से लेकर के जो अभी नेचुरल रिसोर्सेस हो या फिर नैनो मटेरियल, स्मार्ट मटेरियल, कंपोजिट मटेरियल, कई जो अभी मटेरियल क्लासिफाई करने पर आते हैं वो सभी रेंज को कवर करते हुए ये कॉन्फ्रेंस है। इसमें 260 से ऊपर पेपर प्रेजेंट होने हैं जो 6 सेशन में होंगे। पैरेलली और ऐसा 3 कुल 18 सेशन ये 2 दिनों में होना है। हम इस कार्यक्रम के लिए आप सबका स्वागत करते हैं। कोरोना ने हम लोगों को ऑनलाइन सिखा दिया है और लास्ट 4-5 दिनों में जो भी रजिस्टर्ड फिजिकली आने के लिए भी थे उन लोग भी रिक्वेस्ट करके ये किए कि अधिकतर लोग कि सर प्लीज अलाउ मी टू ज्वाइन ऑनलाइन। लेकिन मुझको बहुत खुशी है कि कष्ट सहते हुए भी हमारे जो गेस्ट हैं, हमारे जो चेयरपर्सन्स हैं, वो आज फिजिकली यहाँ उपस्थित हैं। मैं बहुत हृदय से उनका धन्यवाद देता हूं। हमारे बीच हमारे मुख्य अतिथि यूसी मिश्रा जी, सॉरी, हाँ, आप जिंदल JSW BSPL उसमें AVP अर्थात वाइस प्रेसिडेंट, एसोसिएट वाइस प्रेसिडेंट पूरे देश में अपने काम को संभालते हुए जो नए चैलेंजेस जो आज महसूस कर रहे हैं, जो टेक्नोलॉजी के चेंज के साथ में किस प्रकार से नए मटेरियल्स का डिमांड है और कैसे वो अपने कंपनी को टेक्नोलॉजी के द्वारा उस चैलेंजेस को मीट करने का प्रयास कर रहे हैं, उनके अनुभव को हम लोग सुनेंगे। उसी प्रकार से विशिष्ट अतिथि के रूप में हमारे बीच पहले निफ्ट था, अभी नेशनल इंस्टीट्यूट ऑफ एडवांस मैन्युफैक्चरिंग टेक्नोलॉजी, उसके डायरेक्टर श्री प्रोफेसर पीपी चट्टोपाध्याय साहब हैं। हमारे बीच दीपक मजुमदार साहब हैं, सब जाने माने प्रोफेसर। हमारे बीच प्रोफेसर रे साहब हैं, जो बहुत कष्ट सह करके कल 2:30 बजे पहुंचे हैं रात में, और फ्लाइट से दुबई से यात्रा करते हुए कलकत्ता और फिर इधर। मैं सामने बैठे हुए लोगों को देख रहा हूं, रुंगटा माइंस से जेना साहब और उनके 2 साथी, वहां रुंगटा ग्रुप में जनरल मैनेजर हैं। अपने बीच हमारे वरिष्ठ प्राध्यापक VN प्रसाद जी हैं, जिन्होंने यहां से रिटायर हुए हैं। हम उन सब का स्वागत करते हैं। टाटा लॉन्ग प्रोडक्ट के VP डॉक्टर T भास्कर, वो अपने बीच हैं। मनीष झा जी, जिनको राष्ट्रीय पुरस्कार मिला है इलेक्ट्रॉनिक वेस्ट के यूटिलाइजेशन में। अपने उपाध्यक्ष विनोद कुमार जी NML से हैं। ऐसे कई चेहरे को हम देख रहे हैं, हमारे अलुमनाई भी कुछ हैं। मैं सबका स्वागत करता हूं। अपने डिप्टी डायरेक्टर राम विनय शर्मा जी, राजीव भूषण जी, डीन रिसर्च एंड कंसल्टेंसी प्रोफेसर MK सिन्हा जी, हमारे विभाग के प्रोफेसर NML से विद्याधर अरी जी, HL यादव सर, यहाँ के हमारे चौधरी AK चौधरी सर, शैलेंद्र जी, ऐसे सभी वरिष्ठ लोग को मैं हृदय से स्वागत करता हूं कि आज हमारा उत्साह बढ़ाए हैं। इतने दिनों पहला हम लोगों ने 2 नेशनल किया था, ये तीसरा है जो इंटरनेशनल है। मैं विश्वास करता हूं कि आप लोगों के सहयोग से और आशीर्वाद से हम इस कार्यक्रम को बहुत सफलतापूर्वक बढ़ाएंगे, और इसमें से जो पेपर प्रेजेंट आएंगे, और सबसे बड़ी बात, जो अलग अलग इंडस्ट्री से लोग आए हैं, अभी हम लोग बाद में डायरेक्टर सर के साथ एक बार चाय में सब लोग मिलेंगे। उस समय में जो डिस्कशन होगा तो वो एक नया दिशा दिखाएगा कि हमको अपने संस्थान को, उद्योग को रिसर्च ऑर्गेनाइजेशन को मिला करके कैसे आगे बढ़ना है। और हमको लगता है इस कॉन्फ्रेंस का उपलब्धि वो बड़ा उपलब्धि होगा, ऐसे बड़े लोगों के विचार और जो कि देश में पॉलिसी को निर्धारित कर रहे हैं इंडस्ट्री के, ऐसे लोगों के विचार को आने के बाद में मैं पुनः अपने हृदय से अपने निदेशक महोदय को धन्यवाद देता हूं, जो हर क्षण इस कार्यक्रम को लेकर के हमसे अपडेट लेते रहे, गाइड करते रहे और इस कार्यक्रम को सफल बनाने में उनका आशीर्वाद मिलता रहा। आप सबों को स्वागत है। धन्यवाद।
Thank you, sir. Moving forward, I would now request our Honorable Director, Professor Gautam Sutradhar, sir, for his welcoming address and his insights. Sir, please.
Good morning. Good morning, everybody present here. Professor Indranil Manna ji, Honorable Vice Chancellor of BIT Mesra, Professor P.P. Chattopadhyay, Director, previously it was NIFT, but now it is National Institute for Advanced Manufacturing Technology, Ranchi. Our chief guest, Mr. U.C. Misra, Associate Vice President, GSW Steel, Professor Deepak Majumdar, Professor IIT Kanpur, and distinguished guests on and off the dais. I'm welcoming you all for these 2 days International Conference on Advance in Materials Processing Technology, AMPT 2023, organized by the Department of Metallurgical and Materials Engineering, NIT Jamshedpur. What is material processing? Material processing is basically a process which involves complex series of chemical, thermal, and physical phenomena which prepare a starting or raw material to give a shape, to retain its shape, and refine structure and its shape as per the specification given by the customer. Now, the question definitely comes, why it is required? The material processing is basically required to make the product or the component more stronger, more durable, maybe waterproof or corrosion proof, maybe just to increase the aesthetic look or functional behavior of the material or the component. Materials which may be metals like steel, SG cast iron, aluminium, and copper, bronze, etc. Or it may be non-metals like plastics, ceramics, metal and polymer based metal matrix composites, which actually made the tailor-made properties in the composite materials, and processes like casting, forging, welding, brazing, soldering, extrusion, drawing, deep drawing, spinning, and many more others are there, where we are also make the process either it is additive or it is subtractive or it is joining or fabrication by bonding between the two materials by the application of any kinds of energy. It may be thermal, it may be chemical, it may be mechanical. The theme of this conference is related to advanced materials, including engineering materials, smart materials, nanomaterials, biomaterials, materials for the electronics and electrical device, materials for surgical equipments, green manufacturing process, simulation, 3D printing, etc. That means it's a wide variety of area is covered in this conference. Our main objective should make the education system as one of the top destinations for the students, teachers worldwide, attracting talent, fostering the cultural exchange, and contribution to the growth of the knowledge economy. The conference will certainly provide an industry academia platform to exchange their views for the sustainable ecosystem. We, NIT Jamshedpur fraternity, is striving for the vibrant education system to cater the demands not only for the industry but also for the society as a whole, and also to improve the self-reliance with creativity and innovation. As far as my knowledge goes, we have received about 260 technical papers. Out of that, 15 may be on offline mode and 200 papers may be online mode. I'm really happy to announce that our almost first batch of alumnus, he will also in 60-64 batch, I think he is also giving our keynote speaker as keynote speech along with Professor Deepak Majumdar. He is also one of the alumnus of this institute. He will also interested to give some keynote speech. So I'm really happy that very senior alumni will also take part in this conference to support morally as well as physically to grow with this institute. I would like to extend my best wishes for the success of this conference. Also congratulate the organizing team who are working under the leadership of Dr. Ranjit Prasad, HOD, Metallurgical and Materials Engineering, for their tireless efforts to make it reality. I do hope that your stay in Jamshedpur will be very safe and happy. Please be comfortable and ignore any kind of inconvenience occurred due to any unintentional reasons from our part. Thank you very much. Jai Hind, Jai Bharat.
Thank you very much, sir, for your enlightenment in such a kind way. Moving forward, I would now like to invite Professor Deepak Majumdar, sir, a distinguished alumnus of NIT Jamshedpur, has been teaching and conducting research at IIT Kanpur for over 35 years. He was a former chairperson of the Department of Materials, Science and Engineering, IIT Kanpur, and held the distinguished INAE chair and the Ministry of Steel chair successively during the period of 2009 to 2017. Professor Majumdar sir has co-authored 3 books, written book chapters, over 175 scientific articles in the peer-reviewed journals and conference proceedings, a fellow of the Indian National Academy of Engineering, INAE, as well as the Indian Institute of Metals, IIM, and recipient of 50 national and international awards. Professor Majumdar sir has been associated with more than a dozen steel and refractory industry in the country during the past 2 decades. So please.
Good morning, everyone. I was not really aware that I have to make such a speech. I'm prepared only for my talk, which is going to be, I think, presented around 11:20 or so. Anyway, having asked to make a speech or say something, I would like to first show my respect to Professor Chatterjee, Mr. Mishra, Dr. Gautam Sutradhar, as well as Dr. Ranjit Prasad, who are on the dais. I would like to thank Dr. Prasad and his team for organizing this conference. And I was initially in a mood to not travel. I was also thinking of making the presentation online. But one fine morning, Director Sir called me personally, and I thought that it is now my duty, to come over and make that speech in person. I'm very happy to be here. And such conferences which are organized periodically by most of the academic institutes, I am very happy to see that even institutes like NITs and triple IITs are also getting into the foray and trying to organize such conferences periodically. So now that the COVID is over, almost, of course, I think who has not declared it to be over? So I have no authority to say that it's over. So, but it appears that no one is wearing a mask. So I can assume that in spirit it is over. And it is good that we have started to reassemble. And I think it is only when we talk, we meet in person, we share our love, emotions, and knowledge. It is only then when we grow. So with these words, I would like to welcome all of you who are here, who have taken a lot of trouble to come over from distant places, and those who are present here in spirit, like Professor Indranil Manna. And I would like to wish all of them a great day, a great conference here at Jamshedpur. Thank you very much.
Thank you, sir. Now, I would like to invite Professor P.P. Chattopadhyay, sir. He has obtained Bachelor's of Engineering and Master of Engineering degrees from the University of Calcutta in 1984 and 89, respectively, and PhD degree from IIT Kharagpur in 2000. Professor Chattopadhyay has supervised 20 doctoral scholars and published 180 papers in the journals of repute. He has received several awards such as the funding of Gottfried Wilhelm Leibniz program at the University of So please.
Very good morning, Honorable Director, Professor Gautam Sutradhar, Mr. Yushri Prasad, my respected, I should say, colleague and mentor, Professor Deepak Mojumdar, Dr. Ranjit Prasad, dignitaries of the dais, my fellow colleagues at NIT Jamshedpur, participants, and my dear friends. In contrast to what Deepakda has said, when you are heading some office, you are not called for technical session. Rather, you are called for an inaugural session to speak literally do shabd कहने के लिए. So, I would like to request the organizer to allow me to speak for about 10 minutes because I have an intention to share a bit of my thoughts with you for this particular subject, which is not only popular, many of us are passionate about that because we know material is the vanguard of technological progress. I mean, I will try to cover. Technology cannot move an inch without the necessary advancement in materials. And we can see a wide spectrum of frontier in the advancement of material, starting from nanotechnology, in energy sector, hydrogen-based processing, additive manufacturing, and so on. But I thought when we are looking into frontier, it is important to take a look back also to understand the sequence of progress of science, engineering, and technology. For that, I will take an example of solidification processing of material, which is perhaps so far most popular, most versatile, and widely applied processing technique in materials and metallurgy. Solidification processing evolved over millenniums. At the initial stage, during Bronze Age, initial stage of Iron Age, the practice was mostly for making decorative items, ornaments, without the necessity of reproducibility. No one looked for reproducibility when someone is making some ornament or some decorative item. So Professor Manna is here with us now. Gradually, people adopted solidification processing for making utility items like tools, weapons, utensils, with certain extent of performance, with certain extent of reliability, and obviously reproducibility. So this we call practice of craft, and it continued for a long time till first millennium AD. Solidification processing for the first time found its merit for industrial use with the inception of first foundry shop in 1473 at Russia. They called it cannon shop. So this is the first step of solidification processing towards production. At the same time, Thomas Gerhardt at Europe developed type metal. It is basically lead antimony binary and lead antimony tin alloy for making hot typesetting for printing purpose. And this was eutectic, although thermodynamics was not established that time. Gradually, people adopted application of solidification in different dimensions. In 1800, with the invention of arc between two carbon electrode by Humphrey Davy and invention of acetylene gas by Edmund Davy, solidification found a new horizon of its application, that is joining of metals. But so far, the progress was only based on experience gathered by practice, bit of imprecise knowledge, and to some extent, cause-effect correlation. Essentially, there was no foundation of science and fundamentals to look into phenomenology involved in solidification processing until Gibbs published his landmark paper between 1875 to 78, which laid the foundation for phase equilibria. And this was followed by construction of phase diagram of a wide spectrum of alloys. And these phase diagrams classified the solidification reaction as peritectic, eutectic, monotectic, etc., not for the sake of thermodynamic analysis, but each of these reaction was deterministically applied for specific stabilization of phase, design of microstructure, keeping view the target application. For example, we know most of the light alloys are hypoeutectic. That starts with the solidification of primary phase followed by eutectic reaction. The advantage is that we can control the nucleation of the primary phase by use of inoculants, grain refiners, and subsequently we can modify the eutectic phase by using certain modifiers. Similarly, eutectic alloys, as construction of phase diagram progressed, people come across wide range of eutectic alloys, low melting point, which was used subsequently in electronic industries as lead free solders. So that continued for some time. But all these techniques were essentially top down. All the techniques, all the application of solidification processing were essentially top down. And in spite of all the advantages, the difficulty was tracking the process across the length and time scale. When you fill up the mold cavity with liquid metal, you can track the nucleation, growth, formation of shrinkage, formation of defects. This regime is not accessible. So there, with the advent of computational techniques, several models were developed at multi-scale to address the phenomenology at macro scale, mesoscale, microscale, and nanoscale. And all these models were amenable for integration. For example, a macro model, a model for macroscopic scale, say a finite element model, its outcome could be used for a nanoscopic model, say a density functional theory based model, and vice versa. And all these microscopic models, their output was used for macroscopic model. Thereby, this integrated multi-scale modeling framework allowed us to gradually get rid of using empirical knowledge, and increasingly this knowledge was replaced by deterministic science and phenomenology. But still, we are much inclined for understanding things on experimental framework. And here, I'll mention a fact. Professor Gautam Sutradhar and myself are in the same batch. We took admission in undergraduate course in 1980 and graduated in 84. At the same time, an undergraduate student in Texas University, Carl Deckard, from first year, he started thinking of fusing powder material by directed energy beam. He pursued his thought for the 4 years, graduated in 84, and in 86, he submitted his patent for laser-assisted sintering. Not only he achieved the success infusing powder by directed energy beam, but by doing that, he opened up a new paradigm of material synthesis in bottom-up route, which matured into 3D printing technology in 1995 by a group of German scientists. There, we made the metal within the spot size of the energy beam, which we can track and trace. We can track and trace the scan line of the beam. We can track and trace the 2D surface. And we can track and trace the build-up volume. So here we have the opportunity to monitor, to examine all the phenomenology across the length and time scale, and in turn, we can go for dynamic design for in situ compensation and rectification, whatever difficulty we come across in terms of dimension, distortion, microstructure, whatever it may be. So this is basically engineering framed on the science, and that opens the era of engineering science for material processing. I believe we will gradually pursue this particular paradigm when we are going to address advanced manufacturing. Thank you very much for giving me this time.
Thank you, sir, for your maleficent insights. Now, moving forward, I humbly request our esteemed guest, Mr. Umesh Chandra Misra, sir, Associate Vice President, JSW, BSPL. He has a degree in Electrical Engineer from USC Burla, Odisha, and started his career with GE Power in various electrical projects. He is serving to Indian steel industry from last 32 years as a lead agglomeration units. I request sir to come forward and give his views and to the prestigious conference. Sir, please.
Good morning to all of you. The case is the same as Dr. Majumdar told. I was also not prepared for this, but it happened. Respected Chairman of the Organizing Committee, Dr. Ranjit Prasad, and Director NIT Jamshedpur, Professor Gautam Sutradhar, Guest of Honor, Professor I. Manna, Guest of Honor, Dr. P.P. Chattopadhyay, and all the guests coming from various locations, various parts of the country and out of the country, ladies and gentlemen. Actually, I am very much privileged to be here at this NIT conference, and again privileged to be here for my management and our director, Mr. Anil Kumar Singh. Okay. See, we actually first I want to tell you something about our company. We are from JSW BPSL. BPSL means that is Bhushan Power and Steel, which has been taken over by JSW around 2 years back. And the production level has gone up from X level to X plus level or X square level now. Because of the vision our director and CMD is having, so the production level has gone up. Currently we are having at a 3.5 million ton plant at Jharsuguda, as is Sambalpur location. And our vision is by 24, end of 24, it will be 4.5 million ton plant. And by end of 2030, we will be at 10 million ton. That is the vision we are having at Sambalpur plant itself. And if you look at into our JSW as a whole group, the steel giant of the Pan India, then it will be around 50 million ton per annum at 2030. That is the vision our CMD is having. So we are going and we are marching towards that same capacity, how to achieve and how fast we have to achieve. And how the technology can be applied to our all the locations or the plants, and how applying the best technology will get the production, maximum production. That is the aim that we are having. If you will look into Sambalpur plant, that 3.5 million ton, then there are DRI of 2 million ton capacity. We are having a captive power plant of 550 megawatt, and beneficiation 6.5 million ton per annum. Pellet plant we are having 3.5 million ton per annum, and we are having a sinter plant. 2 sinter plants are there, which is having around 6 million ton per annum capacity. Out of which 5 million ton recently we have commissioned. Okay. Then CSP and downstream all the mills are there, WRM, etc. So this is the total capacity of the Sambalpur plant that we are having. Coming to technology, this conference is having advancement in materials processing. Materials mean being in steel industry, we always think material means that is raw material. What is that raw material? Always mind goes to only that iron ore, limestone, dolostone, and coke breeze, coke oven, etc., etc. But here the stalwarts of academia, that from IIT Kanpur, NIT Jamshedpur, director sir, and everybody, they have told so many technology things. But actually, unless academia does not fuse with industry, so both we cannot prosper as a whole. So academia technology is definitely very much required for the industry, and to implement their strength or knowledge in the industry, they require industry also, and the vice versa. Is it true? Yes. So we have to very oftenly we require their help from IIT. We take the help sometimes. Sometimes we take from help from so many NITs how to sort out so many problems that we are facing in the day-to-day activities of our plants. So definitely this is a very good platform in the conference platform where we can deliver our thoughts or exchange our views and take some suggestions from the academia, and from the they can take some suggestions from industry also, where we can prosper as a whole in as a country. Material processing, as I told, suppose you will tell mineral processing, how this mineral processing is going. So my mind goes only to that raw material, as I told you. So that there are 4 stages of mineral processing. How to mine it first? You will mine it first from the larger size to smaller size. That is first stage. Second stage, out of that size, how you will get your required size. That is crushing, sizing and classification. What is that? You have to size it as per your requirement, and you are classify for your requirement. So that is the second stage. Third stage is concentration, where you will get physical and surface chemicals analysis. That is concentration. That is the third stage of the processing. Fourth stage is dewatering. Dewatering means there are moistures in the inherent moisture as well as moisture from the outside world. So where you have to take out the moisture from the minerals or materials as per your requirement to feed to your machine or to manufacture your required material. That is what the processing in brief I can tell you. So after that, so many processes are there, and this is the first process in an integrated steel plant where this is beneficiation, then pelletizing, then sintering, and after sintering, all these materials going to blast furnace, and after that blast furnace, then you are putting it into steel melting sub SMS, and after SMS, you are going for downstream materials where you will get the finished goods. So this is the, I think so many people knows it, but still as a processing, and again, sampling and analysis also is another aspect of processing, where only by doing crossing, grinding, and it will not solve your purpose, but you have to know what is the chemical inside it. Only giving a size from a iron ore rock to 1 mm particle size of iron ore, it will not help unless there is an Fe content is there. So you have to get maximum Fe content out of the mining material, so that will help you in getting the commercially viable material for your use. So that is very much required, or that is very much important, that mineral processing is not only important, that is important when you are getting it separated, which is commercially viable for you. So that is more important, because unless you will get some benefit out of your mining, then it is useless for everybody. So this is something about this steel plant and technology. But in this platform, in this forum, we are industry. I think so many people must be there from steel plants and other plants. So we are here to learn something from this platform. Definitely the advanced technology which are being used and which are to be used if possible, that is to be learned from out of this 260 papers. It is a huge paper, huge number of papers. You have to listen it very patiently. So thank you for an opportunity. Thank you, sir. Thank you, everyone.
Thank you, sir. The conference is being organized in a hybrid mode, that is, both online and offline. So now, in the online mode, Professor I. Manna, the Vice Chancellor of BIT Meshta, has joined us. He has completed his degree from Calcutta University in 1983 and MTech from IIT Kanpur in 1984. Sir did his doctorate from IIT Kharagpur in 1990. He is an academician and a researcher with a wide range of interests in the field of microstructure properties and correlation in nanometric and amorphous solids. He has been awarded the honorary member Indian Institute of Metals Award on November 14, 2017. NMD Award as the immediate past president 2016-17. J.C. Bose Fellow Award from the Department of Science and Technology, DST, and copious other achievements. We welcome you, sir.
Very good morning and namaskar, and I certainly would first like to tender my sincere apology to Professor Sutradhar and all other dignitaries and participants for being unable to join in person. But the anchor already mentioned that the conference allows one to join using a digital platform, and I'm just taking recourse to that. This inability is primarily because I am tied up with our Foundation Day function beginning tomorrow. And many dignitaries and guests have started arriving already. Initially, my plan was to join in person. That's what I promised to Professor Ranjit Prasad. Somehow it didn't happen, but Professor Sutradhar and Professor Prasad let me commit in front of the entire audience here. If you give me an opportunity in an opportune time, I'll be very, very happy to come and spend at least half a day with your students from metallurgical engineering, mechanical engineering, or any other discipline related to closely related to materials, to talk about one single theme called microstructure, which is very close to my heart. And if you kindly allow me, I'll definitely come and address students of all these departments. This is something which I did long back in B College when Professor Chattopadhyay was the head of the department. I took almost 3 hours of continuous lectures. So I intend to repeat that if you give me an opportunity. Now, over to this particular conference, Advances in Materials Processing Technology. I feel privileged that you invited me to speak on this particular platform, and also because of the fact that it is an important topic. There is no other thought about it. And I'll borrow from what I heard Professor Chattopadhyay making a mention about, very nicely trace the history and chronology of evolution of materials. You know, if you trace back, he was very right actually. If you trace back into the history of civilization, starting from the Paleolithic, Mesolithic, or Neolithic period. So I'm talking about a time scale of nearly 500,000 years from now. That's the period from which we have recorded history, from the various archaeological evidences. So since then until today, the evolution of the civilization is very intricately connected with the level of proficiency we have achieved in terms of exploiting materials. So obviously the first material that mankind could lay hand to was stone and earth. And like we say, that invention of fire and wheel were the two major landmarks with which the civilization started progressing. And so since the days of Stone Age, then we had Copper Age, Bronze Age, Iron Age. Then of course the modern times started, and we had in the recent times following the Industrial Revolution, we entered into the Silicon Age, and now we are probably into the nanobio age and so on. So in all these, from most rudimentary to the most sophisticated components that one can think about, they all eventually depend upon the level of performance and exploitation of the material that forms the backbone of the hardware. So when a component fails, very rarely it fails due to the logic or the design. Of course, design errors at times causes major havoc. But generally, for any component, think of an electronic device, maybe a television or a digital camera or the laptop that we use. In almost every cases, when the machine malfunctions, it primarily malfunctions not because at the design board there was certain error in load calculation or conductivity level or heat evolution, but because over a period of time the material started degrading and maybe caused some short circuiting or some other levels of malfunction. So obviously the proficiency of any implement that we can lay hand on will depend upon the performance of the material. So, and where we begin from, I was listening keenly to our colleague from JSW, Mr. Mishra. It's true that when we talk of steel, one way of looking at it is the ultimate spectrum of properties. Like I want this level of yield strength or tensile strength, or maybe this level of ductility or formability and so on and so forth. So, but then in order to reach those numbers in terms of megapascal or percentage or maybe certain impact strength or creep strength and so on. In order to reach that level, you don't necessarily begin at the very secondary steel making process. You actually begin from the mining stage, from where you actually locate through various geological survey mechanisms, the resources, till them out, and then process them, extract the metal value. And you go through very many stages through which eventually you actually end up with the final component. And when you have the material ready, maybe steel, maybe aluminum, maybe some other materials, then it's taken over by the downstream engineering branches of mechanical, electrical, and so on, who eventually give the shape and produce the final component. So the materials processing, I would first address the materials part. We all should be very much aware and completely realize that when we say materials, we are not necessarily talking about metals alone. So if you look at the nature, we basically have three major classes of materials, and very simple way of classifying them will be through the bonding characteristics and simply how the aggregate forms. So any bulk that we think of is made up of either atoms or molecules, and the way they bond with each other could be either by transferring the electron, which is the basis for ionic bonding, by sharing the electrons, which is through the covalent bonding, and by sharing the electrons among the entire continuum, which is metallic bonding. So any material in its purest form will have relation to one of these three possible descriptions. And that's how we have ceramic materials, including refractories, semiconductors. We can have polymeric materials based on covalent bonding primarily, and metallic materials. And out of the metallic materials, we have made our own artificial division, particularly in the metallurgy field. We say ferrous and non-ferrous. Little do we pay attention to the fact that ferrous is iron-based, essentially based on one single element, whereas non-ferrous is the rest of the periodic table. It's not doing justice to the diversity and the possibilities of various metals and alloys not based on iron. But such is the power of iron, because until recently the progress, the economic progress of a country would be judged by the amount of steel produced in that country. I mean, if you look into some of the interesting data, I can quote one at least just to make you aware. At least people of our generation, like Partho, myself, or Gautam Sutradhar, we were born in the 60s. In 1960, India's steel production was 6.5 million tons. Today, we look at 120 million tons. So 2 orders of magnitude greater amount of steel production. Does it mean that it only means that we have found newer and newer resource locations, mines. We have improved our efficiency of extracting iron, and also improved the processing ability of iron into various forms of steel. So there was a time when entire grades of stainless steel, I mean, any alloy steel would be imported. Today, India produces almost all grades of steels, barring, of course, a few of those grades which are of very low volume and not commercially very viable. So we have all the capability of producing all the steels, and also the major alloys, including superalloys, marine steels, and so on. Cost competitiveness is one other aspect which needs to be looked into. Now, to my young friends who are attending this conference as delegates or as scholars and students, I certainly would emphasize that this particular field of materials processing is not only scientifically very relevant, it's actually, it has an element of romanticism. In fact, those who are people like me and Partho and so on, who are physical metallurgists, we kind of are enamored with the notion called microstructure, because if you, for example, a glass of water, you add sugar or salt, you make it sweet or salty. And the more the amount of sugar, the greater the sweetness of the syrup. So this is a way you actually change the character of water, make it a syrup or a salt solution or a saline solution. The same way you take iron, and if you keep adding alloying elements like manganese, chromium, and so on, you will continue to change the character of the alloy and make it more and more amenable to various forms of functionality, starting from increasing strength, increasing magnetic permeability, or improving electrical conductivity or formability, and so on and so forth. But when you do that by changing composition, this is one way of looking at it. But for the same alloy, without making any further investment in terms of creating a new grade, for the same grade of alloy, you actually can change the property over a wide range of anything like, say, let's say we are talking about steel, so anything from 150 megapascal to as high as 2000 or at least over 1000 megapascal. You can change purely by doing microstructural engineering. And that's one concept which is what makes all the difference between the field of metallurgical engineering and the rest of the solid state engineering. So, for example, when a civil engineer designs a bridge or a component or a road or a building, or a mechanical engineer designs a machine, in all the cases, they tend to believe that the design is based on numbers. Little do they understand that a number, let's say 400 megapascal, can easily be made 200 megapascal or 800 megapascal simply by changing the thermomechanical processing routine. At what temperature am I cooling? Artu was talking about solidification processing, that's another way. What is the grain size? How well can I refine the average grain size? What is the temperature in which I am processing, at what strain and to what strain and what strain rate, and how am I cooling subsequently? All these lead to a very significant change in the properties without changing the composition. And this is one branch of science which is mastered by the metallurgical engineers, particularly I would say the solid state people. And that is how today most of the new materials, so-called materials with new properties are emerging. So it's not that every time we change the composition of the steel, we actually tailor or engineer the processing routine, and that's how we make newer and newer range of properties and products. So your topic of advances in materials processing technology is so relevant. That's why I said it's not only relevant, it's absolutely essential for all branches of engineering to understand that hardware ultimately rules, and the hardware is based on certain materials, be it metals, ceramics, or polymers. And in all these groups of materials, if we want to derive the best of the properties and ensure the reliability, then what we must understand the most is not only the composition, but the evolution of the microstructure and its stability. And this is how we actually develop most of the new materials, including the so-called nanomaterials. In fact, that's also another very important point to understand, that the length scale actually defines whether something is giving me one set of properties or another. So the nano is simply the adjective. The noun remains perfectly the same, which is the material. So it is simply by changing the length scale of the crystallized size, you can make a material behave very differently. And that's the beauty of microstructural engineering. The word microstructure is used because when it was coined, we had access only to the optical microscopes and not so much of electron microscope. And with the advent of electron microscope, our power to reach smaller and smaller length scale or go to higher and higher resolution has increased so much so that today we actually very confidently can talk about just a cluster of atoms, even atom scale imaging, atomic force microscopy, and so on. So I think shouldn't take any further time. I actually I had a short discussion with Mr. Sutradhar yesterday, and I said 15 minutes. I'll stick to that 15 minutes. But before I end, I would like to congratulate NIT Jamshedpur, its director, head of the department, Mr. Prasad, and all those who are associated with this conference. That no matter how conventional or rudimentary it sounds, the fact remains that materials processing technology will remain always important so long as we would like to design and develop newer and newer implements and devices and machines. So hardware will rule, and hardware will be always dependent upon the level of performance of the materials associated with it. So thank you very much for your attention, and I renew my pledge that give me an opportunity, I would love to come over and talk to the students of NIT Jamshedpur. Thank you very much. Jai Hind.
Thank you very much, sir, for your magnificent insights and your kind words. Moving forward, as it is already mentioned that we are having both online and offline sessions running together, and few of our session chairs have joined us here in a person. So I would request Director Sir to present Memento as our token of respect. The name of session chairs are Dr. B.N. Prasad Sir, retired professor from NIT Jamshedpur. Sir, please. Proceeding forward, second name is Dr. Vidyadhar Ari Sir, senior scientist from CSIR NML Jamshedpur. Sir, please. Dr. Manish Kumar Jha Sir, senior principal scientist in CSIR NML Jamshedpur. Dr. Sanchita Chakravarti ma'am, chief scientist and also HOD in mineral processing division and analytical chemistry division. Ma'am, please. Now, Dr. Himanshu Mishra sir, retired DGM from Tata Motors. Sir, please.
We would also like to give the token to some of our delegates. Mr. Vikram Jaina, Manager, IOBP Projects. Rungta Group. Mr. Ashok Sahu, AGM, IOBP Projects. Rungta Group. Mr. Santosh Das, Deputy Manager, Iron Ore Beneficiation Plant, Samandipur.
Dr. Mita Tadafdar, Chief Scientist from CSIR NML Jamshedpur. Dr. Jhumki Hayat Ma'am from CSIR NML Jamshedpur. Dr. Vinod Kumar, Senior Technical Officer from CSIR NML Jamshedpur. Preceding to us, Mr. Madhusudan Ray from Dubai. There are copious some other dignitaries with us from JSW, BSPL. So please come forward. Mr. Samal Rai, General Manager, JSW, BSPL. So Mr. Rahul Ragate Sir, Senior Manager, JSW, BSPL. Mr. Ramapati Sir, Senior Manager, JSW, BSPL. Thank you, sir. Thank you, ma'am. Now, I would now like to call upon the convener of AMPT 2023, Dr. Reena Sahu ma'am from Metallurgical and Materials Engineering Department, NIT Jamshedpur, to kindly come forward and give us the vote of thanks. Ma'am, please.
Very good morning to all of you. Respected and our most distinguished chief guest of the day, Mr. U.C. Mishra, sir, AVP, JSW, BSPL. Respected Director, Sir, Professor Gautam Sutradhar. Respected our guest of honor, Professor I. Manna, sir, Vice Chancellor, BIT Mishra. He is joined online here. And PP Chattopadhyay, sir, Director, NIT Ranchi. Dr. Deepak Majumdar, sir, from IIT Kanpur, our HOD, MME, and Chairman AMPT, Dr. Ranjit Prasad, sir, Registrar, sir, all Dean, all HODs, faculty, my colleagues, invited guests from industries and other organizations, CISR laboratories, all participants connected with hybrid mode, means online and offline both mode, and my dear students. I consider a great privilege to propose a vote of thanks to all the dignitaries who have witnessed of this inaugural of International Conference AMPT 2023. It's Advancement in Material Processing Technology 2023 as a memorable and successful of our third series of AMPT. I take this opportunity to express our sincere thanks to our director, Sir Professor Gautam Sutradhar, the dynamic and flexible person in all academic matter, for his immense support and guidance. Thank you, sir. We are extremely grateful to our industry partner like Rampati Mishra sir, Shyamal Rai sir from JSW, Rahul Ragat sir, Senior Manager JSW, or Dr. On Mehanti Bhubaneswar, he is joined online. And Vikram Jaina from Rungta, Ashok Sao Rungta, Santosh Das sir from Rungta, Mr. Madhusudan Rai, Professor Chiranjeev Shahas, Professor Nageshwar Rao. These all are in online and offline mode. So this is seriously for gracing this occasion. His presence here today in this function has immensely enhanced its importance. On behalf of the AMPT 2023 team, I extended my gratitude to AICTE, JSW, Rungta Groups, and Springer, our publication partner, for their wonderful association in the organizing of international conference. I am happy to express vote of thanks to our supporting staff members, technical staffs, and all those peoples who have directly or indirectly made contribution to make this inaugural so exciting. I would like to thanks the volunteer and the secretaries of this association, like Dr. Priyaranjan Mishra, Suruchi, Dipali, Rajneesh, Ranveer. These are all our RS of this DMME department, and few BTech students like Sivani Sagar, Siddharth Sarma, Abhishek Arya, Rishav, Saganik. Sorry, मैं किसी का नाम भूल जाऊँ तो. Okay, and technical, obviously technical staffs, Ujjwal, Kundu, Himanshu, these all are who have running around doing everything required. Thank you so much. My special thanks to Dr. Ram Krishna sir, join our AMPT team this year for this excellent support. I also express my deep gratitude to our HOD DMME. He is also chairman. He always motivated and cordially guided to the students in all the activities, and always check to ensure that things are moving in the right direction. Thank you, sir. Last but not the least, I thank to all the wonderful students or participants present here or connected online who have turned up in such large number. It's 250 abstracts, so it's a very successful number this morning, not only from Jamshedpur, but from different colleges of India as well. We thank you all very much for your cooperation. Thank you, sir. Hope to see some level of excitement in our coming days too during the conference. Have a nice day to all. Thank you.
एक छोटा सा अनाउंसमेंट है। वास्तव में 11:15 बजे हम लोगों का टी ब्रेक था, फिर 11:30 से शुरू था। तो 2 कीनोट स्पीकर है और 11:30 बज रहा है। बहुत सारे लोग ऑनलाइन हैं, तो आप सबसे रिक्वेस्ट करेंगे कि हम लोग इसको कीनोट स्पीच को कंटिन्यू करते हैं और उसके बाद फिर टी ब्रेक करते हैं। जी जी हाँ, मन्ना जी का
I would also like to mention that the gift of token would be sent to Professor I. Manna since he is not available with us now. Now I would request everyone to raise for the national anthem. उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे जय
Everyone is requested to come to the dais for a group photographs. Please. Sir, please. Sir and ma'am, please.
Sir, please, it is kind request because it's a good. सर एक फोटोग्राफ्स हो जाना चाहिए था सर, ये बहुत प्रीशियस मोमेंट है आपने. सो हाँ बैठे हुए प्लीज आप जहाँ पर है वहीं स्टैंड करिए. एक ग्रुप फोटोग्राफ्स आप इस साइड आ जाइए, आप लोग इधर आ जाइए, हम लोग इधर रहेंगे.
Everyone, please stand to your place. We will be having photographs.
We'll have the tea break now. We will have the high tea now. You may proceed outside the hall, first floor lobby for the tea break, for the high tea.
I thought somebody announced that there will be a continuation with the keynote addresses. But there is a second announcement I hear about the tea break.
Just after 5 minutes, you just, we'll go and, take a break and then come back.
Yes, okay.
यहाँ पे लिस्ट नहीं है सर अभी. तो पहले ऑनलाइन में लोग होगा साहब, पहले ऑनलाइन में लोग होगा.
Yes, sir. So after your speech, I would like to take you to the organized center of India. Yeah, sure. Okay. YouTube channel का videos देख रहे हैं सर काफी अच्छा है वो भी मोनेटाइज नहीं है उसमें लड़के कुछ लिख नहीं सकते कि हमको लाइक है डिसलाइक है उसको पढ़ना है वो पढ़ेगा
सर मेरा भी भेजेंगे सर
हाँ मैं आपको सेव कर लूँगा आपका नंबर हाँ श्रीवास्तव धन्यवाद
भेजेंगे सर 2 घंटे नहीं तो किए हैं
केवल बताने के लिए बाहर गए थे ये लोग तो इस खुशहाली में पैदा ही हुए हैं इनको पता नहीं लगा इनको पता लग रहा है कि हम पाए भी दिखते हैं देखो भाई कहाँ लगाए क्या करे अरे एक तारी तो लगाना है देखो बुलाओ किसी को
नमस्कार फ्रेंड्स, आज के डेट में बहुत बड़ी एक उपलब्धि है हमारी इस एनआईटी की, क्योंकि एनआईटी भारत की एक शान है और मटेरियल प्रोसेसिंग टेक्नोलॉजी में एनआईटी और पूरे हमारे इस तरीके के टेक्निकल इंस्टीट्यूट्स का बड़ी दबदबा है पूरी दुनिया में। और आज जो ये कार्यक्रम किया जा रहा है उसी के ऊपर एक बड़ी मैराथन मीटिंग और कह ले तो R&D रिसर्च एंड डेवलपमेंट ये पूरी प्लेटफॉर्म और पूरी
नमस्कार नमस्कार
और आज हमारे
डॉक्टर मनीष कुमार जी चीफ साइंटिस्ट प्रोफेसर मेहरोत्रा के टाइम में हम लोग जैसे रिसर्च फेलो थे उसमें में आपसे 2 बार मुलाकात है ना डॉक्टर राकेश कुमार और
राकेश कुमार तो रिटायर हो गए
नहीं ऐसा धन्यवाद में कर रहे हैं क्या मिलता है ना
अच्छा मेरे पास
और हम लोगों के
आप कहाँ सर
हाँ ये कानपुर में
वहीं पर इमरेटस
अभी मैं 30 जून को रिटायर किया
तब तो भी बहुत है 5 साल तो
हाँ
क्या पोजीशन यहाँ इंडिया को किस तरह रोल प्ले करना चाहिए
नहीं अभी हो जाएगा, केबल ही लगाना है बस।
हाँ अभी के लिए। And keep it no sir, you will miss it then.
No, 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 no. I'll not. इसको कनेक्शन कैसे करेंगे?
Yes. So if you can give it through the pen drive.
No, I didn't bring many pen drive.
Okay.
यहाँ से डायरेक्ट लगाएंगे।
अच्छा रुकिए सर, मैं बुलाती हूँ।
It will better if you can mail us. You need to show something else also. If you just want to present, then you can mail us.
No, but I have no internet connection here.
Sir, I don't know.
Okay. Okay, okay, okay. तुम्हारा
So should I start? Okay. I think it's more than time now. And I have been already introduced, so let us not waste time. So this is the title of my presentation.
I think multiple systems and the code technique. Please ask everyone to come this.
Okay.
All of you, please speak up.
Hello? Hello? This will echo. Okay, fine. Or maybe, I don't need anything. I don't need anything. Okay? Yes. I don't. You just switch off both these. Okay? Yes. Huh? Yes. Where is my presentation gone? Presentation कहाँ चला गया भाई? So, you can read the title of the talk. So, I will be talking about the steel teaming circuitry. Now, I will introduce the subject a little bit. This is a topic which we have started to investigate about 10 years back, and it's extremely important. And my visit to more than a dozen steel industries show that in the last stage of teaming, the argon inertization and the reoxidation of steel is not addressed properly in any of the Indian engineering steel plants, leading to, a deterioration in steel quality. So the thought came to us, and we wanted to make some improvement, and that's what this talk is all about. So we can go to the next one. So I will introduce the relevance of the topic first. And so this is the continuous casting circuitry that you can see. Okay? So you have a turn dish here. There's a ladle. The ladle fits the turn dish, and the ladle and the turn dish are connected by a ladle shroud, which is mounted onto the collector plate nozzle. So the subject matter is restricted only in this part of the talk. That is the ladle shroud, and you can see how the shroud is mounted onto the collector plate nozzle. So it's an enlarged view, and the red thing is the hot metal which flows out, okay, and the shroud is a refractory tube. So this refractory tube is pushed onto the collector plate nozzle, and the molten metal flows through the ladle shroud to enter the continuous casting conduit system. And it is here that when the shroud is mounted onto the collector plate nozzle, the joint is never perfect, because there are two refractory artifacts. So you can imagine, despite all the excellent manufacturing techniques of the refractory industries, we have not been able to completely seal it. Now, as a result, what happens is air from the environment tries to get into the shroud because of the low pressure region which prevails inside the shroud. When a train moves, the wind along with the train also moves. So when the molten metal moves, along with the molten metal, the air is also going to be moving downwards if there is some gap between the collector plate nozzle and the ladle shroud. And this is extremely hazardous and disastrous. It has disastrous consequences in terms of steel quality, as I will show you later on. Okay. So it's an enlarged view here. Again, you can see the slide gate here, the collector plate nozzle, and the ladle shroud. And this shows that initially the turn dish is empty, there's nothing, and then the molten metal starts to be fed into the turn dish through the ladle shroud and the collector plate nozzle. It is these two joints here, the slide gate joints as well as the shroud collector plate nozzle joint. They are, why we are putting in this shroud? We want to protect steel from atmosphere. That is the objective. But that objective is not fully fulfilled because of the imperfections present in these two joints, and as a result of which what happens is atmospheric oxygen and nitrogen tend to get into molten steel, creating all kinds of subsequent problems for us.
And when air gets into the tundish, what happens? The tundish flow, normally in the absence of air, looks like this. And if you have air which gets into the shroud, then the flow gets completely reversed. As you can see, the direction of the arrows here. So we did some water modeling experiments, and this shows that when air comes into the shroud, what happens to the tundish surfaces. And this is a real-life picture where it shows that the slag is separated, exposing the molten metal to the tundish environment, and this tundish environment can also, play an important role because the tundish will also most of the time contain, when the process starts, some amount of atmospheric air in the system. So molten metal getting exposed to atmosphere in tundish can also lead to deoxidation and nitrogen absorption, which can create problem as far as steel. This shows that if you have a tundish atmosphere is not inertized properly. That means you have a chance to pre-fill this space with argon, but if you don't do it, in that case, what happens? Your first bloom will contain a lot of nitrogen, and then the nitrogen content will go down because of the simple fact that the shroud tip is now submerged into molten steel, and as a result of it, there is no exposure of molten steel to the tundish environment. And what happens if oxygen and nitrogen gets into steel, particularly oxygen? So this is the oxygen that we are talking about, which can get into the molten metal in the last stage of steel processing through the shroud, through the collector plate nozzle, and from the tundish environment. And once this oxygen gets into steel, the steel is already deoxidized by aluminum, so the dissolved aluminum remains there. Magnesium comes from various sources, refractories, slag, etc., and it forms a spinel inclusions or double oxide inclusions, and these double oxide inclusions are shown clearly in electron EBSD analysis. And what happens is, when you have these inclusions in good amount forming because of last stage deoxidation, the steel strength goes down drastically, and it shows that we do not tolerate much of these inclusions in the final product, because it will bring down the yield strength of steel from about 1200 megapascal to about 400 megapascal, and it is such a presence of inclusion which might have really caused the snapping of the ropeways, in the mountains of Deoghar a few months back or half a year back. So these inclusions are, detrimental. How does inclusions form? They form because of these oxides, oxygen which come through the little shroud joint as well as through the slide gate joints. And our job is to design, make an improvement in the design so that oxygen from the atmosphere cannot get into molten steel in the last stages. Because we have made a lot of effort to produce clean steel. अगर लास्ट स्टेज में हम लापरवाही कर देंगे, जितना भी अच्छा काम किया सब बर्बाद हो गया. एंड इट इज यहाँ पे जो है द खेल चल रहा है एट द ppm लेवल, 5 ppm, 10 ppm, 6 ppm. That is the level of oxygen we are talking about, and that is going to produce steel inclusions which may be just 20 milligrams in 10 tons of steel. Okay, very little amount, but वो अगर गलत जगह में inclusion बढ़ गया in some sort of a curves or in some sort of a bends, and that's it, the load concentration will take place, and we will have failure or premature failure of the component. And we have seen that yes, if you have problems in the trimming circuitry, if you have little shroud, collector plate shroud joint imperfect, if you have slide gate joint imperfections, nitrogen comes in. Nitrogen का कोई source नहीं है सिवाय atmosphere. We must mind it. Okay. So in the last stage, any increase in nitrogen content is an essential indication that steel has come in contact with atmosphere, and we want to prevent. And जब ये होता है, तब एल्यूमिनियम का concentration जो घटते जाता है, एल्यूमिनियम क्या होता है? एल्यूमिनियम जाके दोबारा एल्यूमिना inclusions बनाता है, and that is the root cause of all our sadness or sorrowness, you may say. तो चलिए देखते हैं आगे जो है क्या है. So now we want to examine the ladle shroud system की क्या problem है ladle shroud system में, क्यों नहीं होता है, we cannot prevent oxygen or nitrogen from getting into the atmosphere. So we studied this, And we found out that there are three typical designs of ladle shroud which people use in the industry. Okay? One is called the multiple gated system, one is called the metallic cane type, the other is a single slot type. And this is the picture of the shrouds mounted in onto the collector plate nozzle as they are being operated in the industry. And this is a schematic of the arrangement. This is the ladle shroud, okay, molten metal flows, and this is the collector plate nozzle, and above here is the ladle, and below here is the condish. Okay, that is the schematic presentation. And so we can draw this top part where argon is being injected. We also inject argon at this joint with the hope that this argon will prevent atmospheric air from going in. Okay, so these are the argon inlets in the three different shrouds. And we have studied how to see that how argon really flows, whether air gets into it or not. So we studied through computational fluid dynamics, and that's the role of modeling in materials processing. Without modeling today, you cannot do any materials processing. Okay, gone are those days when you can just heat treat, change the microstructure, and do something useful. Those are all now done and completed with a reasonable degree of certainty. So with simulation, we have been able to understand that how does the argon distribution as well as air distribution changes. And we can see that this three cross section, what does this mean? This circle annular region essentially represents the white region, the gaps. If you can concentrate on the gap, this is a two-dimensional representation. The gap will go round in a three-dimensional way. That will create the circle. And this is a circle which represents at the top. This is a circle which represents at the middle. This is a circle which represents at the bottom. Green essentially shows that there is a lot of air going in. Red essentially shows there is a lot of argon which is going into the system. There are leakages. So therefore, if you use these two designs, you will have problems as far as oxygen pickup or nitrogen pickup is concerned. This is okay. This is a better design, but this is again not correct because 100% correct, because there you can see a lot of a little bit of green here, a little bit of green there, which essentially means air is getting in. So we thought that can we improve this? We did an isothermal model study and we did a non-isothermal modeling study, and then we see that yes, the trends are same. So one is, you can see, this is the isothermal model. So lower, higher, then lower, higher, and lower. So the trend of the result has nothing to do that whether the temperature of the gas is 1600 degrees centigrade or 25 degrees centigrade. So the trend is reflected identically whether we do any simulation. So these are checks and balances that we perform when we do some industrial scale studies. And then we did some water modeling studies. This is very interesting. And in the water modeling, we studied the distribution of the gas, that if you inject argon around this point, can the argon shroud really this part well so that atmospheric air will not go in, but argon will get in. And that was studied by studying the distribution of potassium permanganate in a submerged specimen. And we found out that three different designs really give rise to three different types of distributions, and this trend, computational trend, is correct, is predicted or currently captured by the physical model studies also. And we also did some submerged experimental studies with the ladle shroud collector nozzle setup. We made some measurements and we validated the model predictions with experimental measurements. So we measured the concentration of potassium permanganate. We predicted the concentration of potassium permanganate distribution within this annular region, which is the shroud collector plate nozzle joint, and at 4 different points we measured the concentration, and we find that our model is reasonably good enough. So therefore, the distribution that I have shown here, okay, can be assumed to be really representative of the actual happenings, and therefore the three different shroud systems are not going to perform identically under steelmaking environments. So we looked at the problem, we designed a new shroud delivery system, and we asked the RHI people to manufacture the shroud. So they did it with an industrial collaboration. So this is, we have now one inlet and two outlets, tangential outlets. You can see these tangential outlets really causes a rotational argon flow within and produces better shrouding effect, which prevents much of air going into the little shroud and collector nozzle. So And we compare the two. This is our new gas delivery design. This is the old gas delivery design. And you can see that our shroud system, new design, ensures more red, which essentially means there is more argon, less of air than the original design's one. And this is the best original design, previous design, and our original design shroud comparison. And here also we find that the original design really produces more grayish color, which essentially means there is more argon inside the system. So these are at different heights here, as you can see here, four different one, and this is along the shroud vertical distance. So this is at the bottom, and this is at the top of it, and this is inside the shroud. So we concluded that laboratory scale results essentially show that our design can prevent shroud oxygen pickup to a certain extent, but won't samjega if we go to an industry and unless and until we demonstrate it. So now we have a Ministry of Steel, Sunflag Iron and Steel Industry, and IIT Kanpur combined project. And in that project we have not me, but the Sunflag people were convinced that our shroud should work. So they approached the RHI, and the RHI made the new design shrouds, and we did the trial with more than 200 hits. And this is the result of the old shroud. You can see the scattered, because they were using 3 different kinds of shrouds without knowing. Kabhi metallic cane, kabhi multiple gated. But we insisted, no, you use our shroud, and as a result of which, what happens is you can see the scatter has come down. These are the new shroud, our design. This is the old design shrouds, and you can see here that in the last 3-4 years, when we started this project, they were having nitrogen pickup as much as 25 ppm. That was 2019, immediately around the lockdown period. Okay, just before the lockdown period, we did this project with them, and today, in 2022, last year, I think they reported a nitrogen pickup of only about 7 ppm or so, which shows that a significant reduction of nitrogen and oxygen pickup is possible by utilizing our shroud design. So here I come to the end of my talk. And so I have demonstrated the power of physical and mathematical modeling, and today we must say that physical and mathematical modeling is of no use unless it can solve a plant problem. Okay? It has to be demonstrated on plant scale, and that we have already done. This is a sapling which I planted in Larsen and Toubro when the company was commissioned, and then about 12 years back, and I think in 2019 again I went, and this little sapling here has grown this big, and they asked me to water it once more. I really feel privileged, and I think we should preserve nature in all our efforts. We have entered an age of what is known as Anthropocene. We're seeing what monsoon havoc is being done. So I think all of us, particularly the steel industries and people like us, should be directing our efforts so that we don't spend too much of energy, do not produce too much of carbonaceous gases into the atmosphere, and make the life of the coming generations much more comfortable. Thank you very much. If you have any question, it's an ongoing study. We are still working, and we are now trying to actually find out that what proportion of steel is being deoxidized because of Tundish environment, because of little shroud problem, and because of the Tundish slag. So we want to calculate this with some plant data. इसका 10% है, इसका योगदान 20% है, इसका 50% है.
Mr. Chairman.
Yes, sir.
I want to make an observation. I was deeply immersed, Omkar Mohanty is my name. I was deeply immersed in the talk by Deepak, Professor Deepak Majumdar, who I always admire. And I was transported into my Tata Steel days. And when I saw those figures of 10 ppm, 20 ppm, or less than 15 ppm in any case, I was very, very impressed. Because the typical value of 30, 35, 40 ppm used to be the norm. Now that he is able to reduce it to less than 10 ppm or 15 ppm, I'm quite confident that particularly in the boron grade steels and so on, it will be very easy now to have this steel. And in the AHSS, generation 3, advanced high strength steels of generation 3, this will be extremely useful because we are heading towards 2000 MPa, that is 2 gigapascal in the UTS level. and the YS level or the proof strength level of the order of 1400 to 1500. So when you, as you go to higher strength, as the Professor Deepak Majumdar said, this work will become more and more important. Thank you very much, Dr. Majumdar.
Thank you, sir. Thank you.
There is a question, can I ask?
Sure, sure.
Sir, I have seen that mild steel is having more problems as far as inertization is considered in comparison to medium carbon steel. Sir, how, like, it is much more pure in comparison to when carbon
These
was
are
created?
mild steel. These are sunflax steel, do not produce any carbon steel. They all produce only special steels, which are alloy steels.
That's what I was trying to imagine, yes.
Okay. So these are now no mild steel. In mild steel business, people are not so worried. These are, all
Absolutely.
engineering and components, and particularly the automobile components, etc., are made by these industries. So a little bit of reoxidation, which is no issue in Tata Steel possibly for certain grades, is always a concern in the special steel plants. That's why I have worked throughout my career with special steels only. Very little with JSW or very little with Tata Steel.
Okay, thank you, sir.
No, Professor Majumdar, these days, the transformation in used plasticity steels, hardenable grade steels, dual phase steels, in Tata Steel and JSW, these have become also very common.
Yes.
Therefore, what you said, they are quite relevant today in Tata Steel as well. Okay.
If not any other question, I may take your leave.
Thank you, sir, for your warm words. Now we have Professor Omkar Nath Mohanty with us. Sir has a BTech and MTech in Metallurgical Engineering from IIT Kanpur.
Kharagpur.
I'm sorry, sir, from IIT Kharagpur.
Yes.
He served as the professor at IIT Kharagpur and is a director level scientist at CSIR NML. We welcome you, sir, to the conference.
Thank you. First and foremost, I extend my compliments to all the organizers, and I was quite impressed by the kind of gathering which you had in the inaugural, and I can get a glimpse of the hall, which is sparsely populated now. So be that as it may, I begin my talk. And it's actually with a sense of deprivation that I start my talk, because I would have liked to be present amongst you all there in Jamshedpur. Unfortunately, I'm not there, so my apologies. So today, give me half a minute to make my presentation part. Share. I don't know if you are able to. Have I been able to project my presentation? Hello.
Yes, sir.
Yes.
You can continue, sir.
So, just hold. Let me make full screen. My apologies again that from an excellent work and mathematical modeling of extractive metallurgy, I was reminded of our mathematical modeling and the R&D in Tata Steel, where similarly at the Tundish salts, the turbulence and streamline flow could be analyzed only with modeling, not otherwise. But I am changing the topic entirely, so my apologies once again to the audience. I am going to the residual stress and connection with the integrity of engineering components. And I will take about 20 minutes to make my presentation. Even the caption slide that you see in front of you with an aircraft, it is not only to decorate the first slide, but actually there is, you can see the landing gears, and below the landing gear, which is short peened, and the short peening process with the robo is also shown. So these are actually the real equipment or components which are used. My scheme of presentation would be these. I don't read that. What I want to tell you is that there are some very interesting examples from the past, and I will take you through that in order to show that how relevant even the past could be. The origin kind. I want to only tell you that residual stress is such an area one can spend the whole life, and there have been people who have spent their whole life. And there are books and books and books on residual stress and its measurement. So in a span of 15-20 minutes, if I want to give you a glimpse, all I can do actually is essentially give you an overview. So that's what I will do after this scheming. In the past, I would bring you to the magic mirrors of China, 200 BC era. So today's terminology should be 200 BCE instead of BC. So the thick bronze discs, etc., and what happened at the Taoguang dynasty, I don't want to delve into too much of history except to say a small anecdote here. And the anecdote is that here is a culprit who was a convict who was actually essentially consigned to death sentence by the emperor. And he was asked for his last wish. And here the convicted person, he says, my last wish is this. He takes out a small bronze piece and he says, I want to put it opposite the sun's rays. That's all I want, nothing else. And it is on a flat surface. He puts it against the sun, and lo and behold, on the wall in front comes a picture. And this was the picture of Buddha. And therefore, everybody is amazed, and the emperor and all his retinue, they fall at the feet of this convict, and they say that you are not only free, we all become your disciples. How did it happen? So that is what about the magic mirror. There are people who have been working on the magic mirror today. You can purchase a magic mirror also from Amazon. So what the magic mirror shows to you is, on one side, there are small relief, and on the other side it is all plain. The other side is all plain. But what happens is, if you put it against very bright light, then it will show actually extremely fine fringes. And these fine fringes are actually basically how micro traces have developed during the casting of the image. So that's the interesting aspect. And if you subject the magic mirror today with the modern magic mirror, the details of the interferogram on the surface you can see. Suffice it to say, therefore, on the one side, if you are casting the contours, on the other side there can also be an impact, which you don't see always unless you try to. So such was actually the importance of residual stress. I say importance, it was not only because the convict could make himself free. In the modern era, it is, as I said, welded structures, landing gears, surface treatment, they are all very important. Essentially, because if I can introduce the right kind of stresses, you can change its fatigue properties radically, stress corrosion cracking properties radically, and so on. If you look at the nature of stresses, what we find is you can have a residual stress, the first kind, second, or the third. We will not get into those details. Those are for scholars working in that area. For our purpose, it is sufficient if we know that there are macro stresses and micro stresses. So broadly, you can imagine the macro stresses are those which are actually operative at a longer distance, much greater than the grain boundary, many orders of magnitude of the grain boundary. And these are of greater industrial or designers' relevance today. And over the entire volume, it is operating. The micro residual stresses are also important, but for today's talk, it is more of the macro that I shall be concentrating on. Although we should be apprised of the fact that there are micro stresses in the smaller systems. These are not just smaller systems, you'll find in functional materials as opposed to the structural materials, the micro residual stresses will be extremely important. For example, if you are making a small thin film and so on, there the micro residual stresses either are going to play havoc or they can bring immense advantage. I have collected some of these accidents over many, many years, and you will pardon my next two slides, which are very difficult to read, but they are not important. You don't have to read each one of them, except to say that here you are talking of failures, number of accidents, due to welding, due to drawing, due to bending process, or due to lining, etc., etc. All these number of accidents cases are there, and there are some case studies which the document should give actually. So, welding residual stresses are most critical actually. If I do not know how to manage, then we have problems. And I will come to that because I belong to an industry today. We manufacture automotive components in 15 different cities in India, including in Jamshedpur. And we know how important the welding residual stresses are when we face the workplace. To the contrary, I can bring in actually beneficial residual stresses in auto gears, lining, as I said, in landing gears. This is exactly what we are doing in our own plant in Pune. We take the automotive gear and then we subject it to short peening. I will talk about it a little later. But what I wanted to tell you was, after the short peening on the gear, you will find that you can actually develop the compressive residual stress up to about 80 to 90 microns. And as those diagrams, bottom right hand side, so the component is hung there, short peening media goes and hits it. And interestingly, all I want to tell you is, the tooth gear of an automotive, what I showed to you, this was not even known to us, that why should we do the short peening? We are doing carburizing, nitriding, boriding, carbonitriding. Each one of them will give compressive residual stress, but not the extent. You will get about 200, 250 megapascal in the compressive load on the compression side. Until the Renault Nissan car came into India about 6 years back, we said we will be giving you the auto gears. They said, can you give us this kind of stresses on the tooth gear at the peak, at the midpoint, at the root, and it has to be such and such value, at the surface at minus 10, minus 20, minus 30, and so on. That's why I started looking into it. We started measuring. Part of that also was measured at NIT Jamshedpur, where we have a portable unit. And then today we are regularly doing it or measuring it at ARAI in Pune. But that's not important how we measure. Most important is that on the tooth gears, you can get minus 1000, minus 1200 kind of megapascal. And for fatigue, they are extremely important. Autofretase is one area which is known for the past at least 50, 60 years. So people know that if you push a mandrel into a gun, let's say, then you will be able to expand it and produce a compressive residual stress. I'm not getting into the details. There are some excellent work in the past 5 years through modeling, particularly from Cambridge University by Professor Bhadesia, those of them who know. Bhadesia used to spend a lot of time at Jamshedpur with our steel. So I'm not getting into the model, etc. But most important is actual measurements which have been done. This is actually taken from Bhadesia's one part of the work. We all knew about the macro stresses and micro, but if you are doing short peening, you are actually changing the volume, expansion you are doing, and therefore you are producing compressive residual stress across the volume. And you can show, I can show here what I showed in the previous slide. Here you are getting the negative compressive residual stress of very high kind, and the cold hole expansion is the example of autofretase. And this is a residual stress after welding. This the stress that takes place in Jamshedpur, our plant unit 2. We make actually 15 and 16 millimeter thick plates. We weld them for excavators, and these excavators belong to JCB, Kobelco, Hitachi, and so on. And we oftentimes land up with the distortion, and this distortion problem you cannot actually solve unless you get into very serious modeling but that's not my talk today. So just to complete this part of the types of stresses, you can have the stresses operative over, as I said, multiple grains, in which case we will call it the macro stress. If it is operating within the grain, then it is the micro stress of the second kind. And if it is operating near the grain boundary alone, then we call it the micro stress of the third kind. But the whole point is the origin. Unfortunately, most of the textbooks do not talk about the origin of residual stress in very clear terms. I want to tell actually my younger friends who are present here, you don't see the stress, neither do you measure the stress directly. What you see in front in the component is actually strain. And it is from the strain you back calculate the stress. This is the point, please remember, those of you who are engaged in residual stress. So therefore, the first two lines are very important. They can arise at every step of the material or component. Whenever there is an unequal distribution of strain, that's very interesting. Unequal distribution of strain, if you do not have, then you will not have the residual stress. Here is an example from our Jamshedpur plant. We used to get from Bokaro these 12 millimeters, 14 millimeter sheets or plates actually. We cut them by plasma. The moment you cut them into three parts, the right hand side portion will meander to the right, and the left hand side will meander to the left, and the middle portion will coil towards you. And all these were happening in Bokaro steel plant until Mr. Mitra, who was the managing director, he once was visiting Jamshedpur, and I had to tell him that this is how we have solved the problem at Tata Steel, by giving actually an extremely thin layer of what we call the liner oil, and that oil can withstand actually extremely high temperature and pressure. And unless you give that oil, you will have this problem. Why? Essentially, because if I am rolling a plate and there is a metal-to-metal contact from the surface to the interior as you go, there is a strain distribution. If you say you are giving a 15% reduction in the rolling meal, number one, let us say, in the hot rolling you are doing, then about 85 to 90% of that 15% is confined only to the surface, near surface. And then as you go down, there will be neutral axis where there will be no strain. So therefore, there is a distribution. And if you have this distribution, then unless you have RBL oil, RBL standing for roll bite lubrication, you are going to get the problems. What does the roll bite lubrication do? It separates the plate from the rolling meal. So there is no direct contact of metal to metal, and therefore through the viscous oil, the stress or the load is transferred, and then your residual stress problem gets reduced. And there are many examples. Quenching after carbonizing, you need that residual stress. But all these are arising because of unequal distribution of strain. So mind you, the point to learn from this slide is unequal distribution. And there are n number of examples, but I don't intend to go through these. With phase transformation, without phase transformation, what happens? So with this phase transformation, if you are quenching from a component from high temperature, you get the thermal stresses, you get phase transformation stresses, and in the phase transformation stresses, you get essentially because there is a volume change from an austenite changes from bauxite to bainite and other transformation products. So this is how the stresses generate. And I will scan through this. This is an interesting example. If you are drawing a rod, for example, and if you are drawing the rod under certain conditions, the same rod, but the conditions are different. Your stresses in the surface, the left-hand side, if you are looking at the first diagram, here the surface is compressive, here the surface is tensile. Here the surface is tensile. Obviously, this is what we would prefer. And this can happen with benign kind of drawing, and this is another better example of machining. We do machining, but how much is the depth of cut? That will decide whether it is a gentle machining or it's an abusive machining. In the abusive machining condition, you find huge amount of tensile stresses in the interior, and whereas in the gentle one, up to about 20 microns, you can have compressive residual stress. So you can actually go on collecting these examples. I was telling you about the volume change from austenite. So there are diagrams available of this kind, and in the same diagram of austenite, you are putting ferrite plus cementite, you are putting martensite. So you can do a lot of interesting modeling if you have combination of these traces, these pages. But basically, what you are seeing here over here is austenite to martensite, because the C by A ratio, which is controlled by carbon, and if it becomes more and more tetragonal, then the specific volume change austenite to martensite is quite high, and therefore you get stress. But if I am confining the transformation only to the surface, the volume expansion essentially will generate compressive residual stress. When the expansion is over, because the backup material is resisting that. This is what you would remember. So the core and the case transformation, how they take place, their MS temperature is different, and therefore when you do a carburizing, this explains why on carburizing you get compressive residual stress on surface, because you have higher carbon on surface, MS temperature is lower, and therefore by the time the case goes through the phase transformation, the core has already gone through, it will not permit it, and hence you get compressive residual stress, etc. etc. Now, how do you measure the residual stress? Now, this is a very important topic, I thought, essentially because of the fact that we measure stress, or somebody can measure stress through various techniques and compare one value with the other. Doesn't tally, and he is quite disappointed. But the fact of the matter is, you are getting information from different amounts of volume. They are not supposed to tally also. One of them is a volume stress, one is a surface stress. And that is the reason why I thought the techniques are quite important. You can go through the earlier techniques, which were hole drilling technique. Those of you metallurgists or mechanical engineers, if you go through Dieter's book, you will find that 1940s hole drilling technique was already there. But if you come to 1990s, then that time he was quite young. Nicolari, a French guy, he comes to Nagpur quite often these days. He has his clients in India. Now he introduced a non-destructive hole drilling. How can hole drilling be non-destructive? Because this is a micro hole drilling technique of Nicolari. So today in NML also, we used to have micro hole drilling technique. It's a very thin hole, so therefore you can plug it. If you want to do the balancing of a rotating component, you can make a hole and the micro hole, etc. You can have laser holography interference techniques using compatible coatings, acoustic wave propagation, Barkhausen noise. I think NML has developed also Barkhausen noise equipment, which is commercially available, and of course the most widely used equipment are the X-ray refractometer, and some of in India we don't use so much, but neutron refraction also is used depending upon the depth from which you intend to have the information. What I want to tell you on this slide is, each one of these techniques can give you a slightly different value. So unless you know how to interpret it, there can be problems. So the material issues, how they affect various techniques. This slide is a busy slide. We don't need to go through this. Suffice it to say, what I have said already, that yes, you can get information about the stress, but you have to make your interpretive capabilities also. The use of strain gauges, for example, that is an ASTM standard on the hole drilling technique. But the stress relaxation that takes place over here, by short pinning if you want to do, and if you want to have a strain gauge, I will show that by short pinning you can actually have the surface residual stress which is negative. But I will show to you at the end of it, the short pinning which we are doing in our plant today in Pune, we are doing the short pinning following the carburizing and night riding. Kindly store this information for the next 5 minutes, because I will come back to that. Why should you do carburizing or night riding before short pinning? If I am getting compressive residual stress already, that's an interesting point I shall deal with at the end of it. So the hole drilling method can be, this is how the hole drilling high-speed air turbine drill can work. It's a very small hole which you can do with this technique, and you can have the data set collected around this short pinning equivalent material, for example, and look at the short pinning values which again which this shows minus 700, that means compressive on the surface. Photoelastic method, this is one of the oldest techniques. All my mechanical engineering friends use this for for donkey's years, so therefore there is nothing that extra that I want to tell, except to tell you that in this technique you can also measure stresses in glasses and also the other transparent materials. You can also make in the opaque materials, but you can have a coating which is compatible, and through that coating you can make the photoelastic techniques. So that's a typical photoelastic isochromatic pattern you get, and you can start interpreting. I am not an expert, incidentally, on the photoelastic technique. So, ultrasonic acoustic wave, I'll quickly deal with. I come to Barkhausen noise. The Barkhausen noise is an interesting technique, and today commercially this unit is available. Those of my friends who know about Barkhausen, if you do a simple pH loop, you'll find towards the end of this loop, suddenly some of the domains, magnetic domains, they will disappear and they will be swapped by the new domains. And the sudden change, or radical change, will give you this kind of discontinuities. And these discontinuities generate acoustic emission. That's what is known as Barkhausen noise. But this Barkhausen noise is extremely useful for stress, because depending on the direction of the stress and depending also on the extent of stress, the Barkhausen noise can change. You can have the Barkhausen noise equipment. This is a typical core of the equipment. You can actually, the Barkhausen noise bus signal looks like this. I will not get into this, except to say that the Barkhausen noise today can measure up to either plus 400 or minus 400, roughly. Thereafter, it is insensitive. This is extremely important. The physics of Barkhausen does not permit us to go beyond plus 400 or minus 400 megapascal, which is where the problem arises if I go to short pinning. So the signal amplitude, etc., of the Barkhausen, they have to be kept in view. I will not go into details. Magnetically induced velocity changes. I will spend 2 minutes on the X-ray diffraction techniques. A, I like it. B, this is perhaps the most important technique for measuring the surface residual stress, which in turn controls the fatigue properties of the components, which are all rotating components, be it aircraft components, automobile components, all of them which rotate. Fatigue is important. And if you have fatigue, which is the controlling mechanism, then we should have depends on peak shift. I repeat, peak shift. Peak shift compared to the what we call the right angle diffraction pattern, to the orientation that takes place, so we take it to various angles, and there will be peak shift, and the peak shift is essentially because the D value in interplanar distance in different directions of the same plane, if you have the same 2-1-1 plane but stacked in different orientations, the D value changes because of residual stresses in interplanar distance. That's exactly what we measure. That is 2 theta perpendicular minus 2 theta phi or psi. So that is the delta 2 theta. But remember, there is a cot theta on the right hand side. If I want to get a high value of the peak shift, that means I want to have a more accurate technique, then in that case my cot theta has to be low. And cot theta can be low only if high angle, which is why I have used their high angle measurement. That is actually a prescription by the American Society of Automotive Engineers or the Society of Automotive Engineers US, SAE. They would say that the peak 2 theta should not be lower than 152 degrees, which is why in ferrite we use a 2-1-1 line and we use chromium K alpha because the angle is around 150. And remember also the Young's modulus E and Poisson's ratio values which are used. These are not, I repeat, these are not bulk values. You must know which plane you are using, and therefore for that particular crystallographic plane, we must know what is the Young's modulus, we must know what is the Poisson's ratio. How to measure them, we will discuss later if you have questions. So the most important thing is, this is how we start. This is how we say this is a perpendicular orientation. Let's say these are the 2-1-1 planes which are parallel to the surface. Then now your X-ray and the detector remain in the same direction, but the sample has started rotating. That means essentially we are talking the same 2-1-1 planes but differently oriented, and see how they are shifted. So this shift is most important, and that's how the principle of X-ray is taking place. And this big shift is what we measure, delta 2 theta, and that gives us this rays. Another interesting point about X-ray, if there is a linear, completely linear, we say it's uniaxial. But if there is a deviation from linearity, then we say there is a shear stress also present. Now this is extremely important for the X-ray stress values which are to be used. Now these are the Young's modulus, Poisson's ratio for different angles. The experts who work in this area, they will be interested. So I'm just showing it for the purpose of showing that it is very important that data on the Young's modulus and Poisson's ratio for different planes are there. Sources of errors, if the grain size is high, the sample dependent errors are there, instrument errors are there, subsurface measurement. If I just now said that penetration is only 2 to 3 microns, how do we measure up to 40 microns? I told you after short peening. So what you do is, for X-ray, there are standard techniques. There is only one textbook also. Go ahead and know one, those of you who are interested. If you go through that, a lot of mathematics is already used. And when you go to subsurface, you remove the top surface, not by mechanical polishing, actually by electrolytic polishing. And each layer that you remove, thickness that you remove, there is an equation that gives you the modification. And we started doing this for our gears also, which we are supplying to Renault Nissan, day in and day out in Pune. Now this is what we do. The short peening, I told you, after the carburizing and short peening. Now I want to spend again 30 seconds here, particularly for my young friends or the scholars who are present here. Why do you do this? Carburizing and nitriding will automatically give you some residual, compressive residual stress. But if you want extremely high residual stress compression, minus 1000, and then inside maybe 1200 and so on, then you have to increase the yield strength first of all. Remember, we cannot lock up residual stress. After all, what is residual stress? There is no applied stress, and yet you are getting some amount of stress inside. And that can happen only up to the yield strength. You cannot have locked up stresses beyond yield strength. You cannot pour more liquid into a glass beyond the height of the glass. After that, if you keep pouring, it will only spill out. Exactly in the same analogous manner. If I want to give more and more deformation beyond yield strength, it will only generate or result in plastic deformation. So which is why we first of all increase the yield strength of that surface through carburizing or carbonitriding, and then if you start short peening, you can lock up more stress. This is an interesting point. This short peening is also, we are doing today short peening there with mechanical short peening, where the steel balls or silicon carbide balls, they will come and impinge upon the surface, and their kinetic energy is known a priori, and then you let them impinge your surface. So there is the red one is plastic deformation, material flow takes place, but there is the elastic spring back as soon as the ball goes back. So you see here the compression. So these compressions are giving you the compressive residual stress and higher fatigue strength. So you see here once again the base condition, let us say with carburizing or some other treatment, the green one will give you the base condition. If I do short peening over that, then I have increased the compressive residual stress further. And that's what is being shown here. So there is a compression here compensated by the inside tension. This is very important. So over the entire volume, the sigma of all such layered stresses is 0. So therefore, we want a compression residual stress. Why? Because all my fatigue, I repeat, fatigue cracks originate from the surface. So therefore, propagation and also creation of these discontinuities on the surface, their chance will go down if I have a compressive residual stress. This is the important part. And today, it is not only the steel ball or silicon carbide, we can do laser peening with stand-up distance. If I have 3 feet, 4 feet stand-up distance, even then with laser ablation, we can also do what is called laser peening. Incidentally, those of you who are interested, there is an international journal which is named short peening. And that journal actually has or deals with short peening, which are actual shots going and impinging. It deals with laser peening. It deals with deep rolling and so on. There are about 4 or 5 different techniques, but the most popular one is the short peening, which shots, steel shots, silicon carbide shots. So in India, we have started using these. And laser peening in India, at least I have not heard of, but all landing gears, I repeat, all landing gears of aircrafts. And these landing gears are made from titanium, aluminum, vanadium. So 6 aluminum, 4 vanadium materials. These are all short peening in order to generate high amount of compressive residual stress. So these are my concluding remarks. These are crucial for some of the structural integrity. You can have beneficial residual stress. You can have damaging residual stress. The damaging ones are mostly negative, the tensile residual stresses, and the beneficial are compressive. Unfortunately, in many industries in India today, we do stress relieving in many of the components without even knowing whether I had a compressive or a tensile. But even if I remove, if I do not know how much I remove, as I was hearing some of the shop floor people, the only stress which is removed is from their mind. Because they feel I have done this stress-free handling now. But on the job, if I have not measured, I do not know how much of stress I have removed. XRD is well established, Barkhausen is quick, hole drilling is necessary for ball stress. I think, thank you very much. I will stop sharing now. Hello.
For mesmerizing presentation. Components.
I'm quite sure. If you use the word mesmerizing,
right? Because I worked on the finding of the residual stress using the Raman spectroscopy technique.
Okay.
And I am also interested to have some data and convert into the model using the machine learning. Thank you very much, sir. Any question? We can go one.